So we're going to let f be a function of u and u be a function of x. Then according to our chain rule, the derivative with respect to x of f of u equals f prime of u times du dx. Now, chain rule. Chain rule is basically allows us to do functions that are too complex to do with simple product, quotient, power function, exponential function, or trigonometric function rules. For instance, let's start off with, I don't care what the letters are, g of x equals the square root of x squared minus 2x. Now, this function is neither power, nor exponential, nor trigonometric. However, with a U-substitution, I could express a function that is. For instance, if I let u be the function x squared minus 2x, then u is a function of x. And if I substituted u into g, I would end up with the square root of u. Now, the square root of u could be rewritten as u to the 1/2. So now I notice that not only is g a function of x with the u substitution, I've made g a function of u where u is a function of x. I can take the derivative of this using my chain rule property at g prime of x equals, this is the function of u. Its derivative is 1/2 u to the negative 1/2. But the derivative of g also includes du dx. Now, I know what u is, so I can, at least for the first part, get that back with back substitution. To get the second component, du over dx, I'm going to find that by taking this derivative, which is 2x minus 2. And now I know this component, and I know this component from there. I'm going to back substitute out the u, and I'm going to back substitute out the du dx, giving me, rotate my camera a little bit, g prime of x equals, I'm going to put a 1 on the top for this, 2 on the bottom, the square root of u, which is x squared minus 2x times du dx, which is 2x minus 2. I'm going to simplify. Also, every fraction must be put in factored form to see if you can factor it, which I can factor out the 2. Oops, sorry. And of course, we reduce that. So my final answer is g prime of x equals x minus 1 over the square root of x squared minus 2x. When we do a u substitution and end up with u being a function of x, basically I want my substitution to be a simple, straightforward formula that I can take the derivative of. For example, au to the n is a power function. I can easily take its derivative. E to the u, the exponential function, very easy to take its derivative. Sine of u, very easy to take its derivative. However, because my variable is not an x, it will always require a second step. So, when I take this derivative of the power function in the form of u, I will take a times n times u to the n minus 1, that's my power function rule, all times du dx. So if I can make something look like a power function with u substitution, I just take the power function rule. With additional step, I need to find du dx. If it's e to the u, the derivative of e to the u is e to the u. But since it's with respect to x, I have my additional step, du dx. The derivative of sine of u equals cosine of u du dx. I did a power function rule. Now I'm going to do an exponential example. For instance, this is no ordinary exponential function. I have a lot of stuff going on in the function. In fact, I have so much going on in the exponent, I can describe it as its own function. So I'm going to let u equal x squared minus 6x. Then f of x can now be written as a function of u, 3e to the u. When I take the derivative of this function, I'm going to use my e to the u's derivative. F prime of x equals 3e to the u times du dx. Since I know what u is, I'm almost done. All I need now is to discover what du dx is. I will find that by taking the derivative of u and now substituting that back into my original derivative. U is x squared minus 6x. Du dx is 2x minus 6. If you're going to leave it in factor form, that's perfectly fine. However, I would go ahead and factor 2 out of the 2x minus 3 so it's fully factored, giving us 6e to the x squared minus 6x times x minus 3. You can also expand that out if you prefer. So I've used u substitution in a power function to make it a power function. I've used u substitution to get a base exponential function. Now I'm going to use u substitution to get a base sine or cosine function or any other trigonomic function you have. Let me do the setup first. So I've got the sine of e to the x plus x. So I'm taking the sine of something a little bit more complicated than a basic input variable. I'm going to get rid of everything inside of there with a U-substitution, where I'm going to let u equal e to the x plus 1. Now I'm looking at f of x equals the sine of u.
Sure, it would be e to the x plus x. Yeah.
Yes, e to the x plus x. Good caps there. That's not a 1. That is a x. So when I take its derivative, f prime of x is going to be cosine of u times du dx. So du dx is e to the x plus 1. Where my mistake came last time, I was too fast and took the derivative already. So I'm going to do a back substitution now. Cosine of u times du, oh, that's an x, times du dx. Okay, I'd like to find the derivative of the exponential function a to the x. This is a little bit more complicated than e to the x. To take this derivative, I'm going to start off by letting y equal a to the x. Now, what I am going to do is, let's see, I'm going to take both sides. Actually, hang on a second. Okay, I'm going to notice that I can rewrite a to the x as e ln of a times x. That's one of the properties you have, exponential properties. So, with that being said, and if you'd like me to show that, I can convert this basically to base e, if you prefer. But that's one of the properties you have. With that, I'm going to do a u substitution, calling this u. Now, realize ln of a is just a constant. So the derivative dy dx equals e to the u times du dx, where du dx equals the derivative of a constant times x. It's just going to be the constant. Now I'm going to back substitute. E to the u is e to the ln of a times x times du dx, which is the ln of a. However, e to the ln of a times x is a raised to the x times the ln of a, giving me the derivative of a to the x is a to the x times the ln of a. Now that we have used u substitution to take the derivative, I can use that property to take the derivative of anything in that format. Now, 4 times 2 to the x. My 4 is a constant out front. It's just going to flow through to the very end. So my derivative of this will be 4 times 2 to the x times the ln of 2. We're done.